Thank you for introducing me. My name is Young Sang Cho. I've been doing this research for about 10 years. I have found that water can be split on solid acid materials. So from that point, I have proceeded my research up to now. Okay, let me begin the presentation. In order to provide hydrogen for the production of hydrocarbons, we need to supply hydrogen source. We happen to use water as a hydrogen source. So in this slide, I introduce water splitting methods other than electrolysis. In 1972, Fukushima and Honda find water can be dissociated into hydrogen and oxygen with the aid of UV light on TiO2. And then 1997, Memorand et al. Experimentally shown that high pressure steam can be split on geolite. And currently, currently to 2011, I have found experimentally as well as theoretically that thermal H2 water splitting can occur once all kinds of solid acid. We thought that there should be some kind of special bonding structure between water and solid acid when solid water is adsorbed on solid acid. So this is an example of adsorption of water on aluminum. We have three kind of bonding structure here. First one, coordinate bonding structure. Second one, hydrogen bonding structure. And third one, doubly bonded structure, having hydrogen bond and coordinate bond together. Among these three bonding structure, the third one, doubly bonded structure, is the most stable. So when water is adsorbed on alumina, more than, I think, 90% of water can make a double bonded structure with aluminum. This is a slide to how to split water. According to Maxwell-Boltzmann distribution, there should be a particle with extremely high energy if high enough temperature is given. This means that when we provide high enough temperature, the coordinate bond and hydrogen bond, electrons in hydrogen bond and coordinate bond can move to conduction band to be a free electron. That free electron can be exchanged and water splitting can happen. Actually, this experiment is very simple. You put solid acid in the reactor and then put a lot of water and then just raise the temperature, and through the you feed some gas into reactor. Then you will have this much of hydrogen production. For example, titanium. In case of titanium, hydrogen production goes up very fast, but diminishes also very fast. But in case of alumina, it produces hydrogen rather slowly, but stay in high concentration, high concentration of hydrogen for a longer time than others. The second picture here shows the cumulative production hydrogen produced. You can see that alumina and silica produce more hydrogen than other solid acid. This slide is shown that even in supercritical condition for water can be dissociated into hydrogen and oxygen on various kinds of solid acid. We try to hydrogen synthesis on solid acids, flow through reactor. In order to prepare this experiment, we pre-tilt the solid acids. We sintered solid acid to remove volatile metals, and then we put into water to remove soluble materials. And then for the experiment, solid acid are placed in a flow through reactor, and then steam was fed into the reactor at room temperature for a possible water adsorption on the solid acid. The temperature of the reactor was raised to 430 degrees C. In this case, gas residence time in the reactor was about 8 minutes. This GC-mass chromatogram is resulted from the experiments on various kinds of solid acid. As you can see, all kinds of solid acid can produce hydrocarbon with water and CO2. We investigated how many hydrogen components were produced on solid acid. This is the example case that hydrocarbons synthesized with carbon dioxide, oxide, and water on aluminum. You can see in the peaks. The peaks represent the hydrocarbon components. At least 52 hydrocarbon components were identified. Among them, 35 aliphatic compounds are found, and 7 cycloaliphatic compounds and 10 aromatic compounds are also found. It is very important to explain the mechanism of how to make a hydrocarbon on solid acid. As seen in this GC applied chromatogram, we have acetylene, ethylene, and ethane were synthesized in the process of reaction. Acetylene can only be synthesized by reaction from CH and CH. Thus, the formation of CH during the hydrocarbon synthesis reaction is quite certain. Similarly, the presence of ethylene and ethane ensures the formation of CH2 and CH3 in the process of hydrocarbon synthesis. In this study, we tested 4 kinds of rocks: basalt, granite, mudstone, and limestone. As seen in this table, all the rocks are dominated by solid acid components in their composition. For all cases, total composition of solid acid materials in rock are more than 85% by weight. These analyses imply that rock can do the same catalytic role as seen in the case of solid acid catalyst. I would like to briefly introduce plate tectonic theory for possible supply of carbon sources to surface rocks. As seen in the picture, at mid-ocean ridge, mantle is slowly erupted to become ocean crust. The ocean crust then is pushed by new mantle eruption and moved toward the subduction zone. During the movement of ocean crust, inorganic carbonates and the remains of biological organisms are sedimented and deposited on the seafloor. These sediment deposits are finally subducted through subduction zone as potential carbon sources for hydrocarbon generation in rocks. This slide shows the results of hydrocarbon synthesis with water and inorganic carbon on basalt. Experiment A with graphite lasts for 75 days, and experiment B with carbon dioxide lasts for 53 days at the reaction temperature of 250 degrees. Conversion ratios from inorganic carbon to organic carbon were about 1.5% for the both cases. As seen in the diagram, major products were hydrogen, methane, and aromatic hydrocarbons. We use a rather big reactor in this case because there can be errors in taking numerous number of samples. That's why we use a 4.77 liter batch reactor in this case. Okay, let me explain possible mechanism of hydrocarbon formation in rocks with water and inorganic carbons. First of all, water will be split into hydrogen radical and OH radical on solid acid components in rocks. And this hydrogen radical then react with carbon dioxide or graphite to produce, as seen in previous slide, CH2, CH3 radical. And then these unstable hydrocarbons and radicals and hydrogen radical can react each other randomly to produce various kinds of hydrocarbons. I think that this is the possible mechanism to generate so many hydrocarbons in the rock. In this case, soybean oil was used as a carbon source to represent the biomass. As can be seen in the second diagram, control experiment without that did not produce any noticeable amount of hydrocarbons. This means that at temperature of 200 degrees C, soybean oil doesn't pyrolyzed, thermally pyrolyzed. So rock can do the some role in pyrolyzing soybean oil. In order to explain the experimental results obtained from the reaction between water and soybean oil, I would like to briefly introduce a paper entitled Thermal Decomposition Mechanism of Some Hydrocarbons. According to this paper, bond dissociation energy for the reaction between hydrogen radical and organic carbon is far less than that for pure thermal pyrolysis. This means that hydrogen radical induced pyrolysis can occur at much lower temperature than thermal pyrolysis. It is also noted that average energy barrier is higher in the order of tertiary carbon, secondary carbon, and the primary carbon. Thus, when carbon-carbon bond breaking occurs, propyl radical was probably produced first, and then ethyl radical second, and methyl radical last. A possible mechanism of hydrogen formation is similar to the reaction between water and inorganic carbons. First of all, water is split into hydrogen radical and OH radical. Hydrogen radical then react with biogenic carbons, organic carbons, to produce propyl radical, ethyl radical, and methyl radical. As previously explained, in this process, CO2 must be produced, and because of CO2, there should be a CH2, CH3 at the same can also be formed. So reaction occurs among these unstable hydrocarbons and hydrocarbon radicals to produce diversified hydrocarbons. And the OH radical, I have to mention here, that probably used for unoxidized part of rock. Oxidizing unoxidized part of rock. Hydrogen production capability of various types of rock were tested. The results were summarized in this table. As you can see, for all the cases, reaction rate and product distribution, etc., are all alike. This means that most kinds of rocks have a capability to synthesize hydrocarbons with water and organic carbons. We also tested the catalytic capability of rocks in supercritical conditions. As seen in the table, in case of using inorganic carbon compounds, aromatic products were dominant. On the other hand, in case of using organic when we use inorganic compounds, aromatic hydrocarbon production is dominant. But if we use biomass, then aliphatic hydrocarbons are dominant in the product. This is the example of hydrocarbon synthesized. Example of hydrocarbons synthesized with CO2 and H2 on basalt. The reaction condition was 400 degrees C and 240 bar. And we performed this reaction for 27 days. And we found 28 hydrocarbon components in this case. This is the example of hydrocarbon synthesized with soybean and water on basalt. We found 42 hydrocarbon components. This is also performed under supercritical condition. Up to now, I explained the reaction between carbon dioxide, between water and carbon compounds on rocks. But according to many references, when you react hydrogen with carbon compounds on rocks, will come up with mostly C1 to C3 linear saturated hydrocarbons. For one case, C5 up to C5 hydrocarbons were found. So it is obvious that the reaction between water and carbon compounds on rocks is quite different from hydrogen and carbon compounds on rocks. Conclusion. First and most important conclusion, water is split into hydrogen radical and OH radical on rocks. Secondly, hydrogen radical can react with carbon compounds for the successive formation of the unstable hydrocarbon species and radicals. These unstable hydrocarbon species and hydrocarbon radicals can react with each other to produce diversified hydrocarbons. Thirdly, thus the formation of hydrogen and abatic hydrocarbons is possible in rocks that are occupied or penetrated by water and inorganic carbon. This implies that petroleum-like hydrocarbons have been produced from the prebiotic era. Fourth conclusion, hydrocarbons synthesized on rocks with water and carbon compounds are consistent with the dominance of saturated hydrocarbons in natural petroleum and the methane in natural gas. Oxygen generated from OH radicals was probably consumed in the process of oxidizing less oxidized constituents of rocks. I think the conclusions of this study suggest that hydrogen and hydrocarbons can be artificially produced by utilizing thermal energy from selected hotspots in shallow subsurface, nearby volcanic or hot spring regions. The storage of carbon dioxide and water, together with biomass in underground nearby hotspots, could lead to the controlled production of hydrogen and methane. Hydrogen might be produced in continuous manner if water and waste oil and organic hydrocarbons were fed into the continuous reactor, which is packed with a more powerfully modified solid acid. Thank you for listening.